In the last video, we learned that the underlying symmetry of our universe is the Lorentz group, not the Galilean group. In this video, I will talk more about the representation of the Lorentz group. To do that, let's look at an example which we have a rod lying on the x direction. Now, what we can do is to rotate the rod, let's call that R, such that now the rod is lying in the y direction. And then we can do a Lorentz boost in the y direction, which will contract the length of the rod due to length contraction. After that, we can rotate back with the inverse element of this R, because for rotation, rotating in opposite direction is just the same as applying the inverse of the element. Then what we will get at the end should be a rod contracted but lying again in the x direction. Now, this whole series of operations should have the same overall effect as if I just boosted the whole thing in the x direction with the same velocity, with the same speed. So from here, what we should see is that the relation between these four operations is that if I apply a rotation, then this boost in the y direction, then the opposite rotation, the result I should get should be the boost in the x direction. So now these four symbols are four different elements inside our Lorentz group, and this equation shows the relation of the four group elements. Now, this formula has nothing to do with the representation. It is just abstract with the symbols. No matter how I represent this group, they should all have the same, they should all obey this relation. Now, one way to represent the Lorentz group is the Lorentz transformation we're familiar with. For the Lorentz transformation, we can have the rotation for 90 degrees as a 4x4 matrix, which the time does not mix with the spatial component, and then the spatial part will rotate. And here we are mixing x and y, so the 90-degree rotation will give you a 1 and minus 1 here. The boost in the y direction will have some factor of gamma in there, because now we are mixing space and time. And we are boosting in the y direction, so we will have some gamma in the y direction. And the result will look like this. Minus sign 0, 0, 0, 0, 1, 0, 0. And for the inverse of the rotation, it will be like this with the opposite sign and 0 elsewhere. And you can do the matrix multiplication to confirm that indeed, if you multiply these three matrices together, it will give you the matrix representing the boost in the x direction. So indeed, this is a valid representation of our Lorentz group, which this one represents Lx, this one represents R, this one represents Ly, and this one is R inverse. Now, is there any way to represent the Lorentz group? For sure there is. So let's consider, instead of this 4x4 matrix, we can represent the R element as a 2x2 matrix with some imaginary number in there. We can have 1 minus I, 0, 0, and 1 plus I over here. And for Ly, we can also use a 2x2 matrix with some hyperbolic function in there. So we can have cos V over 2c, and then here we can have a plus I sinh V over 2c, and then here also, so here it will become minus I sinh V over 2c, and here is cos V over 2c. So we can represent the boosting in y direction with a 2x2 metric instead. For the x direction, we can represent this boost again with some cos and then some sinh with a minus sign here and also here without the imaginary I. So you can go check the multiplication of these three matrices, and indeed it will satisfy this relation. Now you may ask, why are we doing this? Why are we choosing random matrices that satisfy some basic multiplication law? Well, the non-trivial part is that you need to have a matrix correspond to every single element in the group in order to have a complete representation of the group. I can have different angle of rotation and I can boost in different direction. To actually to completely represent a group, you need to have a representation for every single element for any V and any angle you rotate. Now, I'm not going to go into the detail of how to represent this infinite amount of elements in the Lorentz group, but here I hope you can see that these two are very different representations. One is 4x4 matrix and one is 2x2 matrix, and indeed it will have very important physical consequence. Now, here I use some color because instead of this choice of sign, we can choose a different sign for these two sinh over here, and the different choice of sign will give me two different representations of the Lorentz group. The one with the blue sign will be the right-handed representation, and the one with the red sign is the left-handed representation. So these different representations have important consequence when you look at weak interaction. For weak interaction, the weak interaction only act on particles that transform under the left-handed transformation. So you might not heard of handiness of particle because in electromagnetic interaction, the E and M force doesn't care about the handiness of the particle. But when we look at weak interaction, only those transformed in the left-handed representation will be affected. So there are two different electrons. There's right-handed electron and there's left-handed electron. And only the left-handed electron will will be transformed, will turn into a electron neutrino and a W boson. And the right-handed electron will not do that. So we learned that there's different representation of the Lorentz group which do have important physical consequences. And to our base knowledge so far, what we know about our universe is that the underlying symmetry of our universe is the Lorentz group with a SU3 group governing the strong interaction. Now C stands for color because that's the color charge in strong interaction. And there's a SU2L stand for left-handed particle governing the weak interaction that only affect the left-handed particle. And there's a U1 hypercharge, which after spontaneous symmetry breaking governed by the Higgs boson turn into the U1 group of the electromagnetic force. So this is, to our base knowledge, the underlying group of our universe. And the way our universe represents this group is by the standard model particles with the quarks, up, down, charge, strange, top, bottom, the leptons, electron, electron neutrino, muon, muon neutrino, tauon, and tauon neutrino, and the gluon, the photon, the W boson, and the Z boson, governing the weak interaction, electromagnetic interaction, and strong interaction. And there's the Higgs boson that gives all the particle their mass and do the spontaneous symmetry breaking. So this is, to our best knowledge, what our universe is. It is A, this representation of the underlying group of the symmetry of our universe. This is, of course, not the final answer because it doesn't have gravity and it doesn't have neutrino mass, and there's still a lot of unsolved problems. But until now, I hope you understand how important is group theory to physics.